What is Six Sigma? Six Sigma is many things at the same time. It is a business metric, used to compare processes across industries and geographies. It is a statistical measure of variation. It is a methodology, a set of tools and methods, and finally, it is a scientific approach. Let's study all these one by one. The health of a business is measured by a complex array of matrices. For example, EPS shows earnings per share, EBITDA shows the pre-tax revenue, PAT gives profit after tax, operating margin, cash flow, leveraging, valuation, etc. All these metrics serve a purpose, because they are like a measurement tool, and like any measurement tool they vary in their preciseness or level of gauge. There are also countless quality standards and accreditations. Almost all the quality standards and business health metrics display the average health and level of quality at a certain point in time. For a customer, averages do not matter. Single product variations impact a customer. Brand loyalty is very transitory. Hence what is needed is a scale of quality, which measures the capability of the process to perform nearly zero defect work. But, why do we need a quality scale capable of measuring higher than 99% accuracy? Why do we need a high precision metric? To answer this question, let's first answer, how good is good? Most people would say 99% is good enough. Here are a few examples to understand what would happen at 99% efficiency. In the airline industry, 2.1 billion people or 27% of the world's population travels each year. Last year, including all commercial, freight and private aircraft, around 37 million flights happened, carrying 1.2 million passengers daily. Airlines operate at 99.999997% efficiency. If they would operate at 99% efficiency, it would mean 15 long or short landings per day per airport, with at least 6 near-fatal air crashes per day per airport. Let's look at a few more examples. 99% efficiency will mean 200,000 wrong drug prescriptions a year. Within surgery, 99% good would mean 5,000 incorrect surgical operations per week. On the other hand, only 2 incorrect ones would occur if the quality was 99.9997% good. With regards to the financial sector, a 99% good would mean 140,000 incorrect financial transactions per hour, in contrast to only 75 incorrect transactions with Six Sigma standards. That is where Six Sigma, the metric, comes in. As a metric, Six Sigma is a high-precision measure, a scale of quality of a business, and a measure of how many defects will be produced. Higher the level of Sigma, lesser the defects. Once again, as a metric, Six Sigma is a high-precision measure, a scale of quality of a business, and a measure of how many defects will be produced. Higher the level of Sigma, lesser the defects. In other words, Six Sigma is used as a scale of quality. It measures the capability of the process to perform nearly zero defect work. The direction of good is higher the level of Sigma, higher the quality, lower the possibility of defects. Six Sigma I equates to 3.4 defects per million opportunities. It also means a process capability of 99.99997%. Defect is any activity or product which does not meet customer specifications. The maximum number of defects Six Sigma aims to produce is 3.4 defects per 1 million opportunities. It sounds amazing, but that's what Six Sigma certified experts work for. We will understand the methods behind this madness in a bit, but for now, we will look at the next facet of Six Sigma, which is sigma as a measure of variation. Sigma is a Greek word. In statistics, small case sigma is used to show the distribution or spread of data around the average, mean or median. Now, let's spend the next few minutes in understanding some basic statistics concepts. These really are the starter high school stat concepts, and within just a few minutes will help you appreciate the importance of sigma as a measure of variation, and ultimately understand all the key metrics associated with Six Sigma certifications. What is descriptive statistics? Descriptive statistics is a way of describing things about a dataset. We describe the data using some of its properties. For example, if you are evaluating the performance of 2 classes of students, is there something that can be said about the datasets, instead of only just sharing the entire data? Yes, it can be. First, a dataset is described by a lot of its features and qualities, called descriptive statistics, which is followed by making inferences, and this is called as inferential statistics. Now let's think, how will we describe the data? The first description is to find maybe a typical number. which means we want some number that somehow represents the middle. Maybe it is the most frequent number. Maybe it is a number that somehow represents the center of all of these numbers. This is called measuring central tendency. Let's start by thinking of the idea of average. In everyday terminology, average has a very particular meaning. When people talk about average, they're talking only about arithmetic mean, but in statistics, arithmetic mean is only one kind of average. There are different kinds of averages. In statistics, it really means give me a typical, or give me a middle number, or it's really an attempt to find a measure of central tendency. Let's get back to the example. You have a set of numbers, and someone asks you what is the typical score of all the courses in a class. You're somehow trying to represent this set with one number which is somehow typical, or middle, or the center of these numbers. The result of this attempt will give you one of different kinds of averages. As we had mentioned, there are many types of averages. The first is the one that everyone is most familiar with. And that's the arithmetic mean. Arithmetic mean is just the sum of all the numbers divided by the number of numbers we have. For examples, the mean of 15, 10, 25, 20. 15 is equal to the sum of 15, 10, 25, 20. 15 divided by 5, which is equal to 17. Now this effort is called trying to get at a central tendency, which in this case is the mean. The other very typical is the median. Looking for the median is literally looking for the middle number. If we have a set of data, and we order that set, in either ascending or descending, then find which is the middle number, then that is your median. If you have an even number of numbers, the median is the arithmetic mean of the middle two. If you have an odd number of numbers, median is the middle number. Let's look at two data sets. Both these are sorted in ascending order. The first dataset has 4 numbers, and the second dataset has 5 numbers. The median of the first dataset is the arithmetic mean of the middle 2 numbers. The middle 2 numbers are 12 and 16. We add them and divide them by 2 and we get the median as 14. The median of the second dataset is easy. It is just the middle number, which is 12. Now, when do we need a median? A lot of times data is not normal, and outliers exist on the lower and higher side. This is when we need to use both the mean and median for accurate estimation of dispersion. Let's look at an example. We have a data set, 5, 10, 25, 34, 10,000. The mean of this set will be 2014.8. But this will not represent a typical number in this set. In this case the median, which will be 25, will be a more accurate representation. Can the mean and median be the same? Yes, and that is the most ideal situation, which means, data is equal and very symmetrical on both sides of the mean. An example is 1, 2, 3, 4, 5, 6, 7. Here, the mean and median both are 4, and data is spread equally on both sides of the mean and the median. Now, for the third measure of central tendency, the mode. The mode is actually the most common number in a dataset, or, the most frequently occurring number. Which happens only if there is a number which repeats itself. If all the numbers are unique, if there's no one single repeating number, then you have no mode. Let's look at an example. In this dataset, 4 is the number which occurs most often. Hence the mode is 4. In the last section, we talked about different ways to represent the central tendency. Now let's look at the next description of data, the spread. When we measure spread, we are measuring dispersion. The most basic metrics used for calculating the spread of data are range, variance, and standard deviation. We will look at two sets of data, 1, 30, 40, 50, 55 and 101, 104, 109, 110, 111. First, let's take out the mean of the numbers. The first set has a mean of 35.2 and the second set has a mean of 107. The mean, however, is just an estimation of a typical value, and does not tell us how close or far apart the numbers in the dataset are. The first way of calculating the spread is range. To calculate the range, take the largest number, and from that, you subtract the smallest number. The first dataset has a range of 54, and the second dataset has a range of 10. This tells us that the first set is very spread out and the second set is not. However, the range is not a very accurate indication of spread. It does not give a great indication of how the numbers inside the dataset are dispersed. The measures of dispersion seen most often are variance and standard deviation. The symbol for variance is the Greek symbol sigma squared. And standard deviation is the symbol sigma. Hence, Standard deviation is just the square root of variance, or variance is the square of standard deviation. Variance and standard deviation try to answer the question, what is the average distance of how far the numbers in a dataset are from the mean? So, for the datasets shown, let's try and find the distance of each number from the mean. Before that, let's first find the mean. The mean of each dataset is as shown in the table. Let's now find the distance of each point in the first dataset. The numbers in the dataset are 1, 30, 40, 50, 55. The mean is 35.2. So now the distance of each number from the mean is 1 minus 35.2 is equal to 34.2. Calculating the distances in the same way, we get positive 34.2, positive 5.2, negative 4.8, negative 14.8 and negative 20.2. Now to calculate the arithmetic mean of these distances, we add these numbers and divide them by 5. What we get is negative 5.4 divided by 5. Now this is a problem. Because just taking the distances from the mean, we will get either a 0, if the mean is equal to median, or a negative value. This does not solve our problem. To solve this problem, we need to remove the negative sign from the distances. The best way of doing that is taking a square of the number. Hence we take the square of the difference of the distances from the mean, which gives us the numbers 1169.64, 27.04, 23.04, 291.04, 912.04. Now we take a sum of these numbers and divide by 5, we get 470. We do a similar thing for the other set, or in words, we square the distances of the numbers from the mean, add them and divide by the total number of numbers, or we calculate the average of the square of the distances from the mean. We get a number and it is 4. What we have arrived at is, variance. Looking at both these numbers we can say, that the first set is very widespread, and the second one is less dispersed. However, we have to solve another problem here. Variance is giving us a value in square meters, which is very difficult to use in functions. Hence, to arrive at a workable number, we take a square root of the value which we had just arrived. Or in other words, we get the square root of the average of the squares of the distances from the mean. In our dataset we get numbers of 22 and 2. What we have arrived at is standard deviation, which is sigma, which is the square root of variance. Looking at standard deviations of 22 and 2, we can say the numbers in the first set are 11 times more spread out than the ones in the second set. We understood different types of averages, along with the correct measures of shape, variance and standard deviation. We need to understand one more thing, which is the single most important concept in any field. It is called the normal distribution. Gauss discovered that, if we take enough observations, everything in the universe looks like approaching a normal curve, or the bell curve. This occurs everywhere in the universe. For example, the bell curve is seen in tests. The bulk of students will score the average C, while smaller numbers of students will score a B or D. An even smaller percentage of students score an F or an A. This creates a distribution that resembles a bell. The reason for it is the central limit theorem, which says, roughly, that if something results from a lot of small influences, you'll get a normal distribution. Height, for example, is controlled by lots of genes, plus nutrition and other factors. The distribution will look like a bell curve for 99% or 99.9% of the observations. The bell curve is symmetrical. Half of the data will fall to the left of the mean, half will fall to the right. Many groups follow this type of pattern. Heights of people, measurement errors, AHT, CSAT, occupancy, IQ scores, salaries. For now, we just have to remember the empirical rule, or the 68, 95, 99.7 rule. It tells us what percentage of your data falls within a certain number of standard deviations from the mean. 68% of the data falls within one standard deviation of the mean. 95% of the data falls within 2 standard deviations of the mean. 99.7% of the data falls within 3 standard deviations of the mean. First, as we saw in descriptive statistics, the width, or magnitude of standard deviation controls the spread of the distribution. A smaller size standard deviation indicates that the data is tightly clustered around the mean, and the shape will be taller. A larger size standard deviation indicates that the data is spread out around the mean, the shape will be flatter and wider. When we make the standard deviation smaller in width, we do that in 2 ways. First, if there are some data points which are very far away and spread out, or are outliers, we change the activities generating them. This is called as special cause variation removal. Second, if most data points are spread out, we change parts of the normal process to bring them closer to the mean. This is normal cause variation management. We will study this in detail in the measure and analyze phase. Variation management is one of the key goals of Six Sigma management. This finally brings us to the formal definition of Six Sigma. Let's consider an example. A client wants the AHT of the process to have an average of 13 minutes, but it should stay between 10 to 16 minutes. The current AHT of the process is 13 minutes on an average, which meets the client requirement. However, the standard deviation is 3. The other client requirement is the specification limits of 10 and 16. We know our standard deviation is 3. This means that between 10 and 16 minutes we have a width of 2 sigma Oregon, 13 minus 1 standard deviation, that is 13 minus 3, and 13 plus 1 standard deviation, that is, 13 plus 3. We know that this is 2 sigmas long, and from normal curves we know that it holds 68% of the data. Now, even though the process is meeting the average AHT, only 68% of the customers are experiencing the specified AHT. As we had established earlier, customers do not feel the average. Individual variations are their experience. We also know that, if we now reduce the width of standard deviation, we will be able to fit more standard deviations within the client specifications, and hence more customers will be covered. Which means taking steps to make sure more and more AHT is closer to the mean. If our standard deviation is reduced to 1, then with a mean AHT of 13, 10 will be 3 standard deviations to the left and 16 will be 3 standard deviations to the right. Our process will be at 6 sigma. Hence, for a formal definition, when we say that a process, activity or product is at 6 sigma, it means that it will have only 3.4 defects per million opportunities outside the client specifications, and we will be able to fit 6 standard deviations or 6 sigmas in the specification. As we studied in the last section, we can in very simplistic terms, classify 3 main goals of a Six Sigma approach. 1. Normalize a process. 2. Reduce variation, and finally, improve the mean. To achieve these, Six Sigma is also a methodology. Six Sigma methodology is a series of tools and methods used to improve or design products, processes, and/or services for business process improvement and quality management. Six Sigma aims to improve quality by finding defects, determining their cause, and improving processes to increase the repeatability and accuracy of process results. Data-driven, disciplined, fact-based improvement projects are executed with specific steps, in a defined sequence, and with specific improvement goals. The Six Sigma methodology does the following: PP, SP, SS, PS. It takes a practical problem, conducts data-driven fact-based checks to make it into a statistical problem, uses rigorous statistical tools to generate a statistical solution, which is finally implemented as a practical solution. Most quality improvement methods are fundamentally just good common sense. They line up value-creating actions in the best sequence, and performing them more and more effectively. But the Six Sigma process has unique features in its methodology, which sets it head and shoulders above other quality improvement initiatives. A clear goal of achieving measurable and quantifiable financial and quality returns from any Six Sigma project. A metamorphosis of leadership and management into a passionate and committed team. A special process excellence department and team including black belts and master black belts to study, design and implement projects. Transformation of the decision-making process into a data-driven fact-based activity. Elimination of variation and improvement in mean. Creating a high-performance system for business strategy. It provides the framework to prioritize resources for projects that will improve metrics, and it leverages leaders who manage the efforts for rapid, sustainable, and improved business results. Now to why Six Sigma is considered a scientific process. It is because Six Sigma has well-established, scientific methodologies to objectively look at a problem and design solutions, both for existing processes and new processes. We will study the DMAC methodology in this course. DFSS will be covered in a separate course. Now, we will move to the next section, the history of Six Sigma. Six Sigma methodology has scientific models for implementing the Six Sigma methods. Two of the most prominent and widely used are DMAIC and DFSS. Their roadmaps are detailed. At times they vary from organization to organization and also amongst industries. What we will use is a very rigorous roadmap and checklist, which will help you become a very well-rounded and fundamentally strong expert, while still staying nimble and adaptive. What is shown is the roadmap. We will use this roadmap and elaborate each part of it, learn as much as possible all the tools indicated and prepare for projects. Each part of the roadmap will be expounded upon as we move along each phase, from define to control in DMAIC and define to validate in DFSS. We will end the course for today. Be sure to leave comments and contact for any questions, doubts or concerns. For a good understanding, do take our courses on variation, what is P? Descriptive Statistics 101 also. The next course in this series will be on the define phase, along with supplemental courses on the tools required by a yellow belt, and tools required by a green belt.